tabulated a reference value of 25C or 298. And all I've got left inside the integral now is dt over t squared. So that's equal to, it's tiresome to have to keep writing that over and over again, but so that's just the evaluation of this integral. So I can now put the stuff together and write this, get another very useful equation, because this approximation is often quite good. And what we notice is that under these circumstances, the functional form for the log of the equilibrium constant as a function of temperature is very simple. It's just an a plus b over t type of representation. Where slope b has a physical significance of being the heat of reaction over R. So we might ask ourselves, just how well is this going to do for us? Yeah.
I think when you integrated, you might have left out a factor of a negative. The 1 over t minus 1 over 298. From the,
I don't see it.
just from integrating 1 over t squared.
I'm integrating 1 over t squared.
Yeah.
That integrates to minus 1 over t.
Mm-hmm. And the minus might have gotten left out.
God, I don't see anything wrong here.
Well, this, yeah, this, the,
Yeah, 1 over t minus 1 over 298.
Yeah, so I've kind of flipped these guys.
Yeah. Or,
Oh, I see. So what you're saying is maybe this should be minus.
yeah. It looks like the next line you have that.
Yeah. Yeah, thanks. Everything else look okay? Lots of stuff in front of our noses. But if this is, we're gonna get away with this kind of simplistic representation, then we should have a pretty easy way for ourselves to go from our calculated reference value of the equilibrium constant over to some temperature of interest. And the next plot is pretty interesting to go a couple of ways to get to it here. For a number of reactions, now, yeah, that's pretty good, that's big enough for you to see. So let's take some time to look at this. For one thing, it's got, I don't know, a dozen or so reactions on it. And it's plotting log k here against 1 over t. Actually, what we've got here is 1 over t times 10 to the 4. And that takes us, so temperature is actually going up when I go from right to left. So out here, it takes us from 500K up to 2500K. So a lot of reactions. Now, if you took a straight edge up against any one of these curves, you'd find that they're pretty close to being straight lines, but not exactly. So it would depend on just how precise you would want to get in order to be able to calculate an accurate value of the temperature quite a distance away from our reference of 298. But we can see a number of things here. First of all, as I indicated, the slopes of these curves are minus the heat of reaction over R. Now remember, these enthalpies are always heats absorbed. So we have an endothermic reaction if delta H is greater than 0, which means that this slope would be negative for endothermic reactions. So we've got 3 of them here. Reaction of carbon with water, vapor to carbon dioxide and hydrogen, or this other reaction there, are all reactions of carbon with different compounds. Those are all endothermic reactions. And so that means that they would require, the heat will actually be absorbed during the course of the reaction. And opposite to that, we have the exothermic reactions where delta H is less than 0, and that would correspond to ones here where the slope is going up. Now it's tricky, you have to keep your wits about you when you're trying to analyze these kinds of results, because remember, we're going from high temperature to low temperature across this chart. And I think it's evident that if you had data like equilibrium data like this, you could use them to extract values of the heat of reaction by just determining what the slope would be. So that's the first important thing to realize, is this relationship. But there's a couple other things that we can get out of this as well. I can use this as a way of illustrating that we can combine reactions. Let's say I've got the equilibrium constant for 2 reactions that I can combine to get a desired reaction. I can combine log of K in the same way as I combine the reaction statements in order to get the new value, and I can illustrate that here. Well, I'll just leave it at that. I can combine log K values. Let's say, as an example, say that we are interested in the reaction that's not a reaction which is on our chart, but I'd like to know what the equilibrium constant is for that. So let's just say log K for that reaction is something we'd be interested in. But what I can find are a couple of other reactions which I can combine in order to produce this one. Let's just write those down. I'm going to skip writing these phase states because they're fairly obvious. Now, it may be evident that if I subtract 2 from 1, and I'm talking about these reactions now, I will get the desired reaction. Everybody see that? So there are different ways I can make linear combinations out of reactions for which I have information to produce the reaction statement for the reaction that I'm interested in. And this is a simple case where I just subtract this one from this one, and I will end up with this reaction. Yeah. So let's write that. I'm going to just rewrite this. Okay, so let's go look at this one. C plus H2 goes to methane. Here we go, it's this one. Let's say that we're interested in this thing at 625 K. And that'll give me a value for 1 over T times 10 to the 4 of 16. So I'm over here. And I can go up to this reaction at 16 and I get, it looks like log K is equal to 4. Oops, wrong place. let's call that log K1. So C plus 2H2O, let's look at that one. Here we go, it's this reaction. So it looks like I've got log K is -6. So for this one, log K that I'm interested in, if I'm subtracting 2 from 1, so log K3 should be equal to log K1 minus log K2. So what I've got is 4 minus 6 is equal to 10. So the equilibrium constant for this desired reaction that I've got is essentially exponential of 10, or about 22,000, and this is again at my 625 K. But I could put them together at any desired temperature. So if you have a database like the one I've shown here with all of these all of these reactions in it, you can see there's a lot of information there. Then you can put that together in a number of ways to get a lot of things out of it, at least in an approximate form. So I could ask you, what's the heat of reaction of this reaction at a given temperature? You could go there and you could figure it out. Or I could ask you to combine these things to get some desired reaction, which can be produced by a combination of these reactions. And whatever linear combination you make of the reactions, you make that same linear combination of log K's. And you'll get the desired result. Well, our next issue is going to be a complicated one, and that is looking at a particular example. First of all, I'm going to get the equilibrium constant and composition for a particular case where we oxidize sulfur dioxide to SO3. And then we'll look at assuming, first of all, that we have a constant heat of that reaction, and then look at a more detailed one. But that is going to be reserved until Monday. But I want to tell you going forward, my plan is this, and that is to give the rest of the lectures, that is Monday, Tuesday, Wednesday, in PowerPoint form. And I will try to get them preloaded for you so you can take a look at them ahead of time and then have them either on your tablets or printed out. And that will help you with, if you're so disposed, to take notes. I've got Mondays ready. I'm still working on the others, but the hope is that we can have them done, so I'll have them posted for you. So that's it for today. Everyone get a copy of the homework? Yeah.
How much of the homework do you think we can get